Before physics could predict, it had to measure. Before it could measure, it had to decide what to measure and how. This is the turn we trace here, from geometry and craft to experiment and number. Not the erasure of wonder, but its discipline. Not the end of philosophy, but its apprenticeship to method. In Part 1, we treated wonder as a legitimate starting point, attentive, curious, and philosophical. Here we let that posture acquire tools. Archimedes shows how shape can discipline force. Ibn al-Haytham sketches the logic of controlled testing. Galileo slows motion until a law can be heard under the noise. By the end, you'll see why simple contraptions, clear definitions, and shared units change not just what we know, but how we can know it together. What follows is a reader's map. We begin with the philosophy of measurement, operational definitions, units, and instruments, then watch Archimedes extract law from geometry and craft. We pause for the medieval turn toward causal testing, and then sit with Galileo's most radical move, idealization. Along the way, a short detour on scaling laws, proportional to L squared versus proportional to L cubed, shows how counting exponents can reveal necessity. We close with the social technology that makes physics public, error, repeatability, and trust, and a hands-on exercise you can try at home. An instrument is a disciplined question. It constrains the way we ask so reality can answer. Why measure? To say the world is orderly is not yet physics. The leap comes when we agree on a procedure, how to ask, and accept the result, what the world says back. That is measurement. Measurement demands three things. Operational definitions. Mass is not an essence, it is what a balance compares. Time is not a feeling, it is what a clock counts. Temperature is not hotness in the air. It is the reading of a calibrated device that responds to energy exchange in a predictable way. Units. Common sticks and ticks let my meter be yours and my second be yours. Without shared units, arguments collapse into private languages. Instruments. Extensions of attention that trade vagueness for repeatability. They often look like humble contraptions, but they embody a contract. If you follow this recipe, you can check my claim. The moment you write a recipe for how to find a quantity, do this, then that, and read here, you leave mythology and enter method. From then on, disagreement isn't settled by louder voices, but by better procedures. Archimedes, shape, balance, and buoyancy. Archimedes stands as a hinge between pure geometry and physical law. Three threads matter for our story. The lever. Balance is not magic, it has a grammar. Equal moments about a fulcrum. If a lighter weight sits twice as far, it can balance a heavier one closer in. In modern language, the condition is F sub 1 of R sub 1 equals F sub 2 of R sub 2. Geometry speaks and the world obeys. The idea is deeper than a schoolroom seesaw. It tells us that shape, the ratio of lengths, can control force, the method of exhaustion. Archimedes approached the area of curved shapes by surrounding them with polygons and letting the number of sides grow. Truth as limit. Physics will return to this trick endlessly. Approach what cannot be measured directly with a sequence of things that can, then infer the limit. Buoyancy. A body immersed in a fluid experiences an upward force equal to the weight of the displaced fluid. The crown story is less about eureka than about inference. Define a procedure to settle a question. Compare displaced water or compare apparent weight in water versus air, and accept the answer. A method takes the place of a hunch. Across these, Archimedes' genius is constant. Let shape constrain force, and insist that a clear construction yields a clear reading. With lines, ratios, and cleverly arranged apparatus, he pulled law from matter. Craft, tables, and the long fuse. It wasn't geometry alone. For centuries, artisans, navigators, and astronomers compiled tables. Star positions, eclipses, lengths of shadows on gnomons, distances along roads and coasts. These were compressed experience that enabled prediction. The astrolabe, the balance, the gnomon, the clepsydra, they trained the hand to trust procedures over prestige. Two slow lessons accumulated. Regularity invites numbers. When a pattern repeats, it can be tabulated. When it is tabulated, it can be forecast. Skill can be socialized. If a recipe can be written, a novice can follow it. A craft becomes a method. The fuse was long, the flame steady. When the spark of experimentation caught, there was already tinder, instruments, habits of tabulation, and the expectation that nature would answer the same question the same way. Seeing causes, not just correlations. Between Archimedes and Galileo lies another quiet revolution. controlled testing. In optics, Ibn al-Haytham al-Hazan argued that vision is not rays emitted from the eye, but light entering the eye, and he designed experiments to decide between rival explanations. The recipe mattered. Isolate, predict, check. Arrange mirrors and apertures so that only one hypothesis predicts the observed path of light. Then look. Meanwhile, scholastic thinkers wrestled with motion. If you push a cart and stop, why does it keep going for a bit? They proposed impetus, a fading internal motive impressed by the pusher. Still wrong, but a step toward inertia. Motion without a mover is not absurd. It is expected unless something resists. The conceptual ground was softening toward the idea that laws govern change and that we should look for them beneath the clutter of everyday resistance. What mattered was not a single correct theory, but a style. Propose a mechanism, then invent a situation in which only that mechanism could explain what happens. This is the beginning of causal argument that goes beyond after this, therefore because of this. Galileo's break, idealization in the clock. Galileo's leap was methodological courage. He realized that friction, bumps, and air muddle the signal, so he slowed motion down on inclined planes and listened for law beneath the noise. 3 separations changed everything: position, velocity, acceleration. Where you are, how fast you are going, and how your fast is changing are different ideas. Measure them differently. Velocity is not position. Acceleration is not velocity. Idealization. Imagine perfectly smooth planes and frictionless motion, not because the world is like that, but because laws show themselves more clearly there. The model is a lens. It hides the mess so the structure appears. Timing. He turned time from a feeling into a reading. To time slow motion, he used regular beats and water clocks. To refine intervals, he used pendulums and musical rhythm. Time became a variable one could measure and vary. The payoff was a clean relationship. Start from rest on a fixed slope, and the distance down the plane grows roughly like the square of time. In the language codified later, S equals 1/2 a t squared for uniform acceleration from rest. He could predict, he could check, others could repeat it. 2 additional moves often go underappreciated. Thought experiments as probes. If a perfectly smooth ball rolls down from a certain height to a perfectly smooth horizontal, then up another incline, it rises to the same height if nothing dissipates energy. Reduce the slope and it travels farther horizontally before climbing, suggesting that if the surface were perfectly horizontal and frictionless, it would never stop. This is the soul of inertia smuggled in through geometry. Error as data. Galileo was not blind to scatter. He compared runs, averaged numbers, and looked for trends robust to noise. Agreement across different slopes mattered more than any single perfect run. Idealization is not lying. It is how we hear law beneath the noise. What idealization gives and costs. Idealization gives us clarity. It lets us discover proportional to t squared where raw observation shows only irregular rolling. But it has a cost. Every model omits. Friction, air drag, and rotational inertia are silenced in the simplest story. They return later, demanding their due. The art is to choose an idealization that exposes the law we seek without erasing the phenomenon we care about. Ignore air drag to hear constant acceleration, then bring it back to explain terminal speed. Ignore rotation to hear translational motion, then add rotation to understand rolling without slipping. A good model is a sequence of approximations, each earning its keep. Scaling laws, why ants lift cities and giants fall. Galileo also glimpsed the logic of scale. If a creature's length grows by a factor L, its surface area grows like L squared, while its volume and roughly its weight grows like L cubed. Strength depends on the cross-section of bones area, but weight depends on volume. Double the size and you more than double the load. Consequences cascade. Ants can carry astonishing loads because their area-to-volume ratio is generous. Their beams, exoskeleton, scale favorably relative to their weight. Giants must be squat or reinforced. Arches must be thicker as spans grow. Bridges, trees, and femurs reveal the same compromise. The same logic constrains buildings, lungs, blood vessels, and even microchips. As you scale a design, some variables grow faster than others. What works at one size fails at another. This is the first whisper of dimensional reasoning. Track exponents, not textures. You will foresee what rhetoric cannot. Physics will later generalize this into similarity and dimensionless numbers. think Reynolds number and fluid flow. But the seed is already here. Count powers, and the world confesses its limits. Instruments, from contraptions to concepts. A tool is never just metal and wood. It is a protocol. The moment you choose a pendulum, you inherit the ideas of periodicity, small angle approximations, and calibration against a standard. The moment you choose a balance, you commit to comparing quantities rather than trying to perceive them directly. 3 instrument virtues distinguish physics from craft. Calibratability. You can check and correct drift, zero the balance, compare the clock against a reference, swap components to isolate bias. Linearity, in a useful range. Equal changes in the world produce equal changes in the reading. Where the response saturates or curves, you note it and restrict claims accordingly. Portability. Another person can build the same device, follow the same steps, and obtain commensurate results. Knowledge becomes public and transferable. Instruments concentrate theory into a physical routine. A water clock is a claim about flow stability. A telescope is a claim about refraction. A pulley system is a claim about force transmission. Physics advances not only when equations do, but when apparatus embody those equations so that hands can use them. Error, repeatability, and trust. To measure is to meet error. Your timings scatter, your angles wobble, your slope is not perfectly uniform. But error is not failure, it is information. Random error is the jitter that averages out with repeated trials. Take many runs and compute a mean. The spread standard deviation tells you your precision. Systematic error is a bias that repetition will not fix. A tilted ruler, a sticky bearing, a misread angle. Fight it with calibration, control experiments, and cross-checks, different methods agreeing. Trust emerges from a pattern. Repeatability. You can get the result again under the same conditions. Reproducibility. Others can get it using their own gear. Robustness. Slight changes in method or apparatus do not break the effect. Convergence. Independent lines of evidence point to the same parameter value. This ethos is the social contract of physics. Methods anyone can follow, results anyone can test. Humility about uncertainty, courage about claims that survive scrutiny. What changed and what didn't? After Archimedes and Galileo, physics possessed a grammar, define quantities, imagine ideal systems, measure patiently, and write laws that survive repetition. But the older posture remained. Philosophy still whispers questions about order, cause, and intelligibility. We now meet them with instruments in hand. Causality leans toward dynamics, laws that map states into next states. Symmetry will become conservation. If nothing in a setup changes when you shift in time, total energy stays fixed. If nothing changes when you slide in space, total momentum stays fixed. The seeds are already present in the instinct for balance and invariance. Simplicity and elegance become criteria we argue about and test. Simple laws with broad reach are preferred, provided nature keeps saying yes. The ground has shifted. Wonder has learned a new language. Numbers are not the end of awe. They are its grammar. Try this. Measure gravity with a phone and a plank. You can reproduce Galileo's insight at home. You'll need a long, smooth board, a small ball, a book to raise one end, tape, a ruler, and a phone with slow-mo video. Build an incline. Prop one end of the board on a book so the slope is gentle. If possible, measure the angle theta with a phone app or a simple protractor. Mark positions. Put tape marks every 10-15 centimeters down the slope. Number them from the top. Record. Start the ball from rest at the top. Film in slow-mo from the side so the marks are visible. Keep the camera steady. Extract times. For each mark, note the timestamp when the front of the ball crosses it. Scrub frame by frame if needed. Look for t-squared. Compute distances from the start to each mark. Make a quick table with 2 columns, t-squared and s. If the motion has roughly constant acceleration, s will be approximately proportional to t-squared and your points will line up. A straighter s vis t-squared pattern than s vs t is the signature you're hunting. Estimate a and g. Fit a straight line to s vis t-squared, eyeball is fine. The slope is roughly 1/2 a. Solve for a, then estimate gravity by g almost equals a over sine theta. Reduce noise. Repeat 5-10 runs, average corresponding times. Smooth the track, paper tape, and clean the ball to reduce friction. You should see your scatter shrink while the line slope remains similar. Sanity checks. Increase the angle slightly. Your A should increase, and your G estimate from a divided by sine theta should stay roughly the same. Switch to a heavier ball. If rolling friction dominated before, the scatter and slope may change a little. Note what changes and what stays stable. Write a brief note in your notebook. Which change, smoother surface or more repeats, help more? What remained consistent across your variations? That consistency is what physics calls a law peeking through the noise. Method, law, and the promise of order. Archimedes and Galileo did more than solve puzzles. They changed the terms of knowledge. They turned qualities into quantities, hunches into procedures, and private insight into public method. Once you demand operational definitions, shared units, and repeatable measurements, argument shifts from who is right to what survives the same question asked the same way. That shift is the foundation on which everything that follows will stand. They also separated kinematics, how things move, from dynamics, why they move, a conceptual split that clears the stage for law. Galileo's S proportional to t squared is a kinematic pattern extracted by idealization. It invites a dynamic explanation, some constant agency producing constant acceleration. The lever turns shape into constraint. The inclined plane turns time into variable. The square cube insight turns scaling into prediction. Each move extracts a structural invariant from noisy experience. Equally important, they made knowledge portable. Instruments encode theory into routine. Anyone who follows the routine can check the claim. Error becomes visible and therefore negotiable. We average, we calibrate, we cross-check. Trust is no longer a property of authors, it is a property of methods. That social technology, the public, repeatable experiment, is why physics could become a community project rather than a lineage of authorities. This matters for what comes next. Newton will take Galileo's cleaned-up motion and write the grammar that binds it. Inertia as a universal backdrop, force as cause, and proportionality between the two. F equals ma. Archimedes' lever becomes torque. Galileo's idealized motion becomes the test case for a law. The method of exhaustion blossoms into calculus, a language of limits fit for change. The same insistence on invariance will mature into conservation principles. When nothing changes in time, energy is constant. When nothing changes in space, momentum is constant. We will name these carefully in Part 3. If you want a single takeaway, take this. Method is the covenant between curiosity and the world. Define what you mean, idealize to hear the signal, measure with care, and let the results stand, even against your preference. That covenant is why simple lines on paper became predictions about comets, tides, and falling apples. Why this foundation matters. Clarity. Operational definitions turn vague concepts into measurable quantities. Lens. Idealization reveals law by temporarily silencing noise. Publicness. Instruments and procedures make knowledge reproducible and transferable. Honesty. Error is information. Quantified uncertainty deepens, not weakens. Trust. Scalability. Dimensional and scaling arguments stress test ideas before heavy math. Invariance. Early instincts about balance and uniform acceleration foreshadow conservation laws. Next time, we use this grammar to write our first full sentence. We'll state Newton's 3 laws as axioms, show how they organize motion into a coherent system, and introduce just enough calculus to see why a law like F equals m turns patterns, Galileo's S tilde t squared, into predictions about worlds from sliding blocks to planets.